Hello and welcome to Temporal Facing Part 4, the Twin Paradox. In this video, I'm going to be using an app I wrote in Mathematica to describe and resolve the twin paradox of relativity. The twin paradox is quite simple. We have a stay-at-home twin who stays at home, marked here by the path O to D, and we have a traveling twin who travels, visits a space station for a short time at event E, and then returns home to point D. What causes the consternation is a general rule of thumb called time dilation that is usually misapplied to the twin paradox. Time dilation basically says that moving clocks go slower than stationary clocks. For instance, let's say that the stay-at-home twin ages 4 years while the traveling twin is on his way home to event E, or is on his way from home here at point O to event E. I'll turn on the Earth time isoclines and adjust the scale until it says so that we've got four units of time from point O. 1, 2, 3, 4. Now let's look at the isoclines of time for the traveling twin on his outbound journey. Counting off, I see it is 1, 2, 3. It's just a little bit more than 3 years for the outbound twin. Then, looking at the isoclines for the inbound twin, it is 1, 2, 3, another 3 years. So, it took 8 years, 1, 2, 3, 4, 5, 6, 7, 8, for the journey in the perspective of the stay-at-home twin, but it only took 3 plus 3 from the perspective of the traveling twin. Now the paradox comes from imagining things from the traveling twin's point of view. In order to look at that, I'm going to adjust the temporal facing of this diagram so we can see that point of view on the outbound journey. Now you can see that the traveling twin experiences about 3 years as he goes from event O to event E. But what is the event that the traveling twin sees as simultaneous with event E? It's over here. And let's show events A, B, and C. You can see that this event A is simultaneous with E. Now we can show the Earth isoclines and Earth time isoclines and see how much time has passed between point O and A. We see it is about 2.5 years. Only 2.5 years have passed between O and A for the stay-at-home twin. So now let's adjust our temporal facing again and have a look at the return journey. You can see now from the perspective of the stay-at-home twin that only 2 or 2.5 years pass between events C and D. But from the perspective of the incoming twin, there are about 3 years passing by. 1, 2, 3. So, from the perspective of the traveling twin, about 2.5 years pass for the stay-at-home twin while he's going from point O to A, and about 2.5 years pass for the stay-at-home twin while he's going from point C to D. So, indeed, during those 2 parts of the journey, the stay-at-home twin's clock is going slower than his. But if you didn't notice from the animation and discussion, we have neglected to include all of the events that happened to the stay-at-home twin between event A and B. Because what really happens is that during the turnaround event, events A, B, and C swing around from the traveling observer's future into their past. Now, you may be hearing about this for the first time because around the turn of the millennium, 2000, there was a paper written about radar time and radar distance. I'll just show radar time for the moment. But the basic idea of radar time was if the traveling twin sends out a radar signal, a time-stamped radar signal, and it reflects back, then he can find the time at which the reflection event happened by taking the time the signal was sent and add the time the reflected signal was perceived and divide the sum by 2. Now this procedure is exactly the same as what Einstein used in his 1905 paper regarding non-accelerating observers. So within certain domains, this gives you the same thing as you get from temporal facing. For instance, the coordinates of all of the events in this region, which is the past light cone of event E, are the same as the coordinates of the outbound twin. And the coordinates of these events, which are all the events in the future light cone from event E, are the same as the coordinates of the same events in the perspective of the inbound twin. However, the events to the left and to the right are calculated by sending out a signal and waiting for a return signal, sending out a signal on the outbound trip and waiting for a signal on the inbound trip, essentially calculating the coordinates based on an emitter and receiver which you know perfectly well has not been held steady during the measurement. Ostensibly, there were 2 reasons that the idea of radar time and radar distance were developed. Number 1, they wanted to provide isoclines of time that did not cross each other, and they succeeded. None of these isoclines of time cross each other. However, none of the other labelings of time cross each other either. The isoclines of time for the stay-at-home coordinates are parallel straight lines. The outbound time coordinates are parallel straight lines, and the inbound time coordinates are parallel straight lines. Another thing they were concerned about is that these let's fix it that way. That faraway planets would swing forward and backward in time every time anyone goes dancing. Now, if you want to call that a problem, you can call that a problem. But let's see if radar time actually fixes this problem. No. You can see that putting new labels on the events in question does not prevent them from swinging forward and backward in time. Now, in the time since On Radar Time and the Twin Paradox was published, it has been widely adopted as accurate, and it never actually says anything incorrect. However, when I say it doesn't say anything incorrect, it comes really, really close to saying incorrect things. For instance, while they never actually conclude that they have prevented the time isoclines from swinging forward and backward, they make it sound as though that is the entire point of their paper. Sorry for carrying on about that. I just wanted you to know why you have probably not heard about temporal facing before. It is because Dolby and Gull are just two among a fairly vast group of authors on relativity theory that do not acknowledge that events actually change their location during a Lorentz transformation. In all of the peer-reviewed journals, you will never see this transformation actually being done. You might see this diagram and this diagram and this diagram. They might extend the axes and put labels on them like this, but you won't actually see this diagram or this diagram because they do not generally accept that events actually move in the point of view of an accelerating observer. Well, that's all for part 4. Once again, I hope you will like and share. Come visit me at www.spoonfedrelativity.com, and thank you for watching.